So in our previous video, I already showed that square root of 2 is not a rational number. Today, I'm going to give a more formal definition. I'm going to start with introducing the Dedekind Cut on a set of rational numbers, and then we're going to move forward with the gaps between rational numbers and real numbers. So let me just first get started with the introduction of Dedekind Cuts and what it is, because this is an important subject. This is an important thing to understand before getting started with understanding the completeness of the real set. So to begin with, I'd like to show you a couple of simple examples. Let's say we have inequality a is less than or equal to 1. This is one of the simplest examples that you can ever think of. So this is basically the number a, which is the variable a sometimes in a general sense, which takes some values which is less than or equal to 1. Then we can introduce two sets. Let's introduce the set a, which consists of values a such that they is less than or equal to 1. All right. And at the same time, I'm going to define the set a prime. A prime is going to be the set of values a1, or a prime, sorry, and a prime is greater than 1. All right, so we have two sets. What is the main property of these two sets? The main property is that if we try to find the intersection of these two sets, we can see that their intersection is an empty set. And another property of these two sets is actually the fact that their union of these sets is the set of rational numbers, because we are considering them over our set of rational numbers that we defined 2 videos before. And we can also see that for any number, this is the third fact, this is the third property, for any number which is in our set A, and for any number which is in our set A prime, we can see that A is less than or equal to 1, which is less than in turn than A prime by definition. This is by definition. And from this, it follows that A is less than A prime. I'm not going to prove why. This is called transitivity. This is called transitivity of inequality. I'm not going to prove this part and why this holds, why that implies this an equation. This is called transitivity of inequality, and I'm going to cover this in my future episodes, not right now. But this is a useful property that you have to, take into account. So we basically have defined two sets, the set A and set A prime, and they're kind of splitting the set of rational numbers into two classes. In fact, these two sets are called classes. The class A is called lower class, and the set A prime is called upper class. And the fact is that these two sets, these two classes, or their union, forms a set of rational numbers, and the number 1, which divides the set of rational numbers into two classes, the upper one and the lower one, is called the cut. So there is such alpha, which is in this case is 1, such alpha number, which is the cut of set of rational numbers into two classes, lower one and upper one, A and A prime. So this is called a cut. This is a definition of, this is the split of rational numbers. So what is so special about that? Well, in this particular case, when we have A is less than or equal to 1, there is one interesting thing. The thing is that our lower class A has a maximum element, which is 1. And we can actually show this. We can show that for any A which belongs to A lower class, A is always less than or equal to 1, which in turn less than any value from A prime, which kind of points out to the fact that 1 belongs to lower class, and at the same time, 1 is the greatest element in this lower class, which means that 1 is the maximum in our lower class. On the other hand, if we try to consider the upper class A prime, and if we take any number from A prime, we can see that A prime is greater than 1. There is a density property that between 1 and A prime, we can also find another rational number. Let's call it, for any prime, there exists a rational number x such that, right? This is the rational number such that x is greater than 1 and less than a prime. This is a density property. Again, this is the second property that you have to keep in mind. I'm not going to prove it right here. This is not the main point of this video. I'm going to make another video about these two properties. We just have to keep this in mind, that between two rational numbers there is another rational number. But we can put there. We can actually show this. We can construct this using decimal notation. I'm not going to do this right now, but this is something useful. And given the fact that this x is actually greater than 1, it means that x belongs to a prime by definition of what a prime upper class is. But at the same time, we can see that for any a prime, we can always find such x. That means that there is no minimum element of a prime. We can conclude that there is no such minimum element of a prime. So the moral of this story is that if in this particular cut we have a maximum element in the lower class, but we do not have a minimum element in an upper class. In fact, we can introduce another cut. Let's say a is greater than 1. What does that mean? That means that we have another cut, a prime, where a consists of elements a, which are less than or equal to, or let's better call it greater than or equal to 1, where a consists of elements that are just less than 1, a less than 1, and a prime is consisting of elements of a prime such that a prime is greater than or equal to 1. Then we can show that a prime has a minimum number, and the a has doesn't have a maximum number. It doesn't have the maximum number, which is interesting. And this is also a cut. Its union equals to a set of rational numbers. It is a cut over the rational numbers. So this is the Dedekind's cut. Now let's take a look at the other example. Let's suppose that we have a cut a and a prime, and let's assume for a second that there is a maximum element in the lower class and a minimum element in an upper class. Let's call it a0, which equals to maximum in a, and a0 prime, which is the minimum element in upper class. Then we know that this is the union. The rational set is the union of these two sets, a and a prime. And then for any c, which belongs to this union, it belongs to one of the sets, a or a prime, it belongs to this. Now let's take such c that it is less than ao and greater than ao and less than ao prime. That is possible by density property. And it should belong to one of these, by definition, it should belong to, for any C rational, it should belong to the union of A and A prime. But in this specific case, since it is greater than A0 and less than A0 prime, it is kind of greater than maximum possible element in A, and it is lower than lowest possible element in A prime. So it doesn't belong to A and A prime. But this is the contradiction. That's just a contradiction. That means that C doesn't belong to A union A prime. That being said, it is not possible that both our classes in our cut have maximum possible and minimum possible element. They should have either, right? Yes, but there is one small wrinkle here. Let's consider the following example. We already proved before in our previous episode that the square root of 2 is not a rational number. We already proved that. So what if we consider numbers a square, for example, less than or equal to 2? Oh no, not equal to 2, less than to 2. So in this case, we can define two sets. The set A is the numbers A, which are, well, let's say they are positive, and a square is less than 2. And let's do the same for a prime, which would be by definition a such positive that a square is greater than. In fact, we can see that their union equals to the rational positive numbers and 0. Well, quite intuitive, right? Square root of 2 doesn't belong to this set, but it is not a contradiction because we already know that square root of 2 is not a rational number, so that's all good. But this number still exists, and there is still a gap. And the fact is that we can even show that there is no maximum number in a lower class, and there is no minimum number in the upper class. How to show that? So here it is. Let me show this. When we're stating that there is no maximum number in the lower class, we're essentially saying that for any number which belongs to the lower class, there is always such, let's call it n positive, which belongs to the natural positive numbers, such that a square less than 2 logically implies that a plus 1 over n square is less than 2. It is kind of because, i.e., a1 plus n is greater than a. So we're essentially saying that for any a, there is always greater a, which also belongs to the set, but at the same time, it is smaller than 2. That means it also belongs to a lower class. So there is no maximum in lower class. So if you want to prove that, we just need to show that such n exists for any a. We can find such. So let's just resolve this inequation. That should be a squared plus 2a1 over n plus 1 over n squared less than 2, which means that 2a1 over n plus 1 over n squared less than 2 minus a squared. We can see that 2 times 1 over n plus 1n squared is less than 2 1 over n plus 1 over n. That said, i.e., if our 2a times 1 over n plus 1 over n is less than 2 minus a squared, then our initial inequation would be true, plus 1 over n squared will certainly be true, is less than 2 minus n squared, a squared. But from this inequality, we can see that 2a plus 1 over n is less than 2 minus a squared, which is equivalent to n is greater than 2a plus 1 over 2 minus a squared. That said, for any a, it is sufficient to choose n large enough that this inequality holds, and then our original inequality holds as well, and consequently a plus 1 over n squared would be less than 2, but at the same time it is greater than just a, which implies that there is no maximum element in our lower class. Using the same kind of reasoning, we can conclude that the upper class doesn't have the maximum element, i.e., for any a, we have to introduce from a prime, we have to introduce such n, which is positive, natural that a plus minus 1 over n square is greater than 2. And then let's resolve this equation. We have a squared minus 2a over n plus 1 over n squared, 2. And then we can see that a squared minus 2 is greater than 2a over n minus 1n squared. And then we can see that a over n is greater than 2a over n minus n squared. Therefore, if 2a over n is less than a squared minus 2, that would logically imply that a squared minus 2 is greater than 2a over n minus 1 n squared. Nice. So we just need to choose n large enough such that n is greater than 2a over a squared minus 2. If we choose such n, which is the positive natural, then we can conclude that there is such number a minus 1 over n in square, which is greater than 2. And it is less than just a, which means there is no minimum element in the upper class, lagging a little bit. That kind of means that there is no prime element here. There is no minimum element in our prime upper class, right? So summarizing this video, the main point is that if we have a Dedekind, then over rational numbers, over a set of rational numbers, we can have 3 possible options. We either have maximum in our lower class, but there is no minimum in our upper class, or we have minimum in our upper class and there is no maximum in our lower class, or we have a situation when we don't have neither maximum in our lower class nor minimum in our upper class. So that's only 3 possible scenarios over rational numbers. And in the latter case that we just considered here, we concluded that if there is some sort of gap which is introduced by real number, such as square root of 2, when we don't have neither maximum nor minimum in lower and upper classes accordingly. So this is the Dedekind's construction, and we're going to rely on this Dedekind's construction in order to derive the completeness of the set of real numbers.